is about the BPS spectrum of Argyres-Douglas series spectral network. So during the talk, I will explain these three terms one by one. And this work is done with one of my colleagues in Caltech and published on arXiv in September. So in the beginning, I'd like to explain this thing, the idea of our work, by showing a biological analog. So suppose we start with, we look at these two animals. One is polar bear, the other one is panda. So they definitely look different. I mean, they have different colors, different shapes. They live in different places of the moduli space. Well, one is in the North Pole, the other one is in China. But well, if you look at their bones, they don't really look so different, right? And although, well, you may treat them as two different animals, but if you count the number of bones and the structure of bones, they say, oh, they're actually the same thing. They are just a bear. So yeah, that's the idea, basic idea. So it's although two seemingly very different things, can actually, if you look at some deep structure or some signature, you found out that they may just be the same thing. So just as Masaki-san mentioned in the morning, so there are many things that can be redundant or delusional. So, well, in this case, the thing that really captures the animal is the number of bones, maybe, well, which is called the Witten index in our language. You know, sometimes if you purely count the number of bones, it may not be enough. So you may need a refined index, which is kind of the bones on the hand. Okay, so let's back to business. So if we think about this problem in physics, so what is the most basic observers? So it's of course the spectrum is one of the most basic observables. For example, if we have flame path or emission spectrum, which can test which element do we have as a sample here. And very early in the classic example is always the hydrogen computation of hydrogen spectrum. But in general, it's really difficult to get the full knowledge of the spectrum of the given system. And we also have trouble thinking about the perturbative spectrum and non-perturbative objects, for example, electrons and magnetic monopoles. But in one case, finding spectrum might be much easier. That's the case with supersymmetry. When we have supersymmetry, there are particular states called BPS states, which is annihilated by some supercharges. And since these states are supersymmetric, from superalgebra, we know the mass of the states is completely determined by the central charge. And the mass of this states is protected by the supersymmetric algebra. So usually, no matter you tune the parameters of your theory, as long as it still have the same charge, which is usually the case, the mass of the states didn't change too much. However, there is it cannot change continuously with the parameters, but there is a spectral phenomenon called wall crossing. So it looks like if you look at the whole parameter space, the BPS spectrum is piecewise constant. So I will talk about the wall crossing phenomenon later. So so as we see, the spectrum is kind of a good indication, a good sign, a good observable of the theory. So these two theories, which looks very different, but after some analysis, we found they have the same spectrum. There is a very good chance that these two theories are just identical. We're just looking from different aspects of they just have two different heights. So how do we find spectrum for supersymmetric series? The tool we're using here is called Spectral network. So this spectral network can give BPS spectrum of 4D n equals 2 class S series on Coulomb branch. So if we can identify series with BPS spectrum. So usually it's important and useful when series are strongly coupled and we don't have a good perturbative understanding of this series. So here are examples of spectral network, and from this spectral network, we can identify something called objects called S-walls, and from S-walls, we obtain the BPS states and its central charge. So the outline of my talk is first tell you what is spectral network and how do we compute this, and then define the object I'm studying, which is a n equals to 2 superconformal field series, and in particular the Argyres-Douglas type series. Then I will give some examples of application of spectral network in such series. But well, I guess since I'm constrained here, I probably will only go through a few of these examples, and then I will conclude. So what is spectral network? Consider some theory which is a kind of unfibering wrapped on some two-dimensional manifold Riemann surface C here. So this is here is our unfibering, and this square is our Riemann surface. This unfibering can wrap on this Riemann surface many times, and resulting a four-dimensional series. So there can be M2 branes suspended between different branches of unfibering. And if we project this M2 branes on the Riemann surface, this M2 brane looks like a one-dimensional object, one-dimensional walls, which we call S-walls. And this S-walls, by definition, it has two indices, because each M2 brane is connected to with two branches of unfibering. So we have one index dedicated to one branch, and the other index dedicated to the other branch. So the true definition is the true definition we requires a Seiberg-Witten curve. So this Seiberg-Witten curve is a multi-shaded cover on the T-plane. And on this T-plane, we have Seiberg-Witten differential lambda equals x dt. And then this S-wall connecting the i's branch and j's branch is defined by the following flow equation, which is a Seiberg-Witten differential on the i's branch minus Seiberg-Witten differential on j's branch, and dt over d tau. D tau is a parameter. Parameterize the S-wall, and this e to the I theta is some constant. Theta is some constant, and later we will find that this theta is the phase of central charge of the BPS states.
Theta is always real?
Yes, in this definition, theta is real. Basically, there's no sense. If theta has some imaginary part, it's just we can just rescale it by redefine the tau here.
Does theta also carry double indices, or is it uniform?
No, this theta just is just one parameter here.
On the left hand side, you have ij information.
Yes. So that means I already said that the S-wall has ij information.
So theta is uniform with respect to ij. Does theta carry ij indices also?
No. So this for given ij, this theta just gave us a family of S-walls solutions.
tau is not related to complex coupling, right?
No, tau is free from
line.
theta. Yeah. So let me. So start from this usually this would start from a branch point or a supersymmetric joint and flow generally to a puncture on the Riemann surface. So all the S words, when we changes I and J, all the S words at a given value of theta, and we draw all the S words, the collection of all the S words is called spectral network. So yeah, this theta is independent of Ij. So let me show you an example. This is the simplest example of a spectral network construct around the branch point of a ramification index 2. The Cyber-Witten curve is just a t equals to x squared, and this is some surface covered the complex plane twice, and the branch point is 0 and infinity. So on each sheet, the Cyber-Witten differential is square root t or minus square root t, and given theta, we have a flow equation for S was, but you can see that since in this case S12 and S21 is almost the same, except it's minus sign here. So once we got solution for x12, we automatically know the solution of s21. So if we solve the solution, we actually get 3 solutions, because here the solution t is exponential 2I theta over 3, and when we rotating theta here from 0 to pi, we actually we say this S will just rotate only 120 degree. So we can, this is one wall, and we can rotate theta pi degree, and we get another solution and the third solution. So this is on the Riemann surface, and if we draw all the branches like this, so the S wall looks like this one, and this one. So in general, around the ramification, a branch point of ramification index n. So we just have start from some branch point, and just it can more and more S walls coming out. So the total number is determined by the ramification index n here. So the whole spectral network, it rotates only by this angle when we change theta from 0 to 2 pi. So that's determined by the solution here. So also in some complicated case, there can be multiple branch points, and from each branch point locally, it always looks like this. Some S walls coming out from the branch point, and but globally, this different S walls can collide, and from the place that they collide, they can they have extra S walls, but they have to satisfy the BPS condition. Lambda I1 I2 plus I2 I3 plus lambda IN I1 has to be 0 to preserve supersymmetry. So yeah, so since we know the BPS spectrum, spectral network, then how do we determine the BPS states? So as we can see, that from the knowledge of Cyber-Witten curve, we know BPS states corresponds to a cycle on the Cyber-Witten curve. And then if we change the theta parameter here, as we can see here, if we change theta, the spectral network here will rotate slowly. And at some point, we will have multiple S-words, and we locate theta. This usually the S-words come from some branch point that goes to infinity. But at some certain theta, certain critical theta, these two S-words might collide with each other and become some S-word from one branch point to some other point. And the whole S-word has a finite length. So, for example, here, when theta is smaller than a certain angle, this S-word is infinity, this S-word extends also to infinity. And at certain value, this comes closer, and then collide and combine into one word from one branch point to the other one. And if you go past the critical theta, this S-word becomes flows to infinity. So at this, since these are two branch points on the Riemann surface, and at this critical theta, this finite S-word reference a cycle on the Riemann surface. So since this is a cycle, this corresponds. So finite S-word corresponds to a BPS state. And the central charge of this BPS state is just the Cyber-Witten differential integration of Cyber-Witten differential along this cycle, which is the S-word. And we can show that from the equation here, which we know that the phase of Z is just theta critical here, and the mass of BPS states is just the length of S-word here.
So in the context of Cyber-Witten, what does the index ij mean?
Oh, so this
Different gauge groups?
no, this Cyber-Witten curve is just it's always some cover of some base Riemann surface, right? So this different ij is
the label of different sheets.
Yeah.
So when the theta is not at the critical value, that's what cycle being shot on. So you are saying when theta equals theta critical, that's when cycle is stable?
Actually, it's when theta equals to theta critical, you can some S-word matches with the cycle.
Okay.
So in the other case, you say it's all like infinity, so it seems like it's winding to infinity. It's not a closed cycle. So this thing doesn't refer to a closed cycle. So only in this case, you see this is corresponds to some cycle around the branch point. So okay, let me have a review of the series I'm studying, which is N equals 2 superconformal field series, and in particular the Argyres-Douglas series.
So the range of ij is related to the range of gauge groups. How many sheets in the spectral curve has to do with the range of gauge groups?
Yes, and together with some other factors. I mean, for example, if for Argyres-Douglas series, I'm considering it. It depends on the puncture types on the Riemann surface. So, as Masakito mentioned in the morning, so there is a large class of four-dimensional series obtained by 6D AN-1 2,0 series, compacted by this series on a Riemann surface, and R1, 3. And in this case, the resulting four-dimensional series has N equals 2 supersymmetry. And the property of the Riemann surface, together with the rank AN-1 in 6D, determines the resulting 4D series. And the low energy effective series is determined by Cyber-Witten curve here. So we see to answer your question before, so we say that Xn, which is the kind of rank of how many branches in your Cyber-Witten curve, is determined by the 6D run here. And this x and t coordinates belongs to the tangent bundle of the Riemann surface. And the moduli of a case differential is just a Coulomb branch moduli. And separating differential is like this, and central charge of BPS state is the integral of separating differential along a cycle. So this on this Riemann surface C, we can have punctures, which are codimension 2 defects on the Riemann surface. And phi on the puncture, this holomorphic, this differential k differential phi becomes singular on the punctures, and each puncture is labeled by a set of by n-1 numbers from d2 to dn, which is just determines the singularity of this differential on each puncture. Yeah, I guess I had a typo here. So the singularity is determined by this number here. Okay, so then from the singularity of the differential phi, we know the singularity of separate differential at each punctures. And look at the maximal singular term here. We can classify the punctures into two types. One is called regular puncture, which lambda has at most a single pole on the puncture, and in this case, the residuals are mass parameters of the flavor symmetry. The other type is irregular puncture, which of course means lambda has a higher order pole on each branch. So we can denote the series by this rank of 60 series, the Riemann surface, and the type of punctures. Then the thing that I'm working on particularly is called Argyres-Douglas series. So these are isolated fixed points of SUN pure Yang-Mills series in 4D. And they are isolated fixed point means they don't have any how do we say this? They don't have any exact deformations, exact conformal deformations. Yes. Yeah, it means there's no modular space for this. Okay, so they happen as so when two mutually non-local particles, or in the or we can say it's the electrons and the monopole pairs become massless at the same time. So if we construct it from a geometry construction, so that means we compactify the 6p2 gamma 0 series on a Riemann sphere. We consider sphere only with an irregular puncture here. And the Cyber-Witten curve in this case is always an unsheeted cover of the sphere. And one nice thing of this series is it has only the BPS spectrum is always finite, so it's easy to analyze, but it has no Lagrangian description. And we can classify the Argyres-Douglas series by the type of irregular punctures and if we have extra regular punctures. So, for example, in A1 case, the singularity, the Cyber-Witten curve is x squared plus is phi 2. So the singularity of Cyber-Witten differential always translates to the singularity of phi 2. If then one class is a sphere with only one irregular puncture, if the order of this irregular puncture is always the singular, the maximal singular term is always n plus 5 of phi 2, then this series corresponds to Argyres-Douglas fixed point of SU n plus 1, smaller n plus 1 pure Yang-Mills. And then if we add if we add regular punctures here, we get something. We can get flavor symmetries here. So this corresponds to some fixed point of some super Yang-Mills and plus some plus quarks.
Why did n plus 5 is not lower?
Sorry?
In the case of one irregular puncture,
Mm-hmm.
the order has to be greater or equal to 6, right?
Yeah.
Greater than 6. N is greater than 1, so n plus 5 is greater than 6.
Yes.
So why is
So
that? Why can you go lower?
so that means so that means you certainly need so this differential is x dt, right?
Yes.
Which is square root phi 2 dt.
Yes.
And so you need at least square root is greater, at least square root is t to the 2 or above to get irregular puncture, right? So that means the order of phi 2 is at least 4 or above. But I believe if you take a 4 or 5, yeah, I think in this simple case, if you take just 4 or 5, it still becomes something trivial. Okay, any more questions? So yeah, so here you need some higher order to make it to make the Sacrovita differential, well, more singular on this one. So for AN case, we still have we also have a classification of one irregular puncture case, or some one irregular puncture with some regular puncture case. So so in here we see this. There is one case that even we start with a n minus 160 series, and if we find some certain type of irregular puncture, again it gives the fixed conformal point of SUN pure Yang-Mills, which means this construction, which we from a n minus 1 type 6D series and compactify some weird irregular puncture here, gives us the same infrared series as a compactification of Riemann surface of A1 6D 2,0 series. So that means we start even start from different 6D series and different type of geometry. In the end we probably get the same thing. So if I summarize all these classes, so it seems from 60A1 we have this some types of class, and from 60AN we have another type, but in the IR it gives the same BPS flavor. Or actually we can prove that they gave the same series. We can have some other case, and again from two different constructions we arrive at the same series. So there are tests of this conjecture that the different construction gives you the same series. So one test is testing central charge and some other things. So our test is testing if we compute the BPS spectrum, these two different constructions actually gives you the same BPS spectrum. And